So let's get started with this final video that relates to the resolution theorem. So the resolution theorem is a central theorem in linear programming because it allows us to devise an alternative way of representing polyhedral sets. And even though it might not be practical at first, it's actually central. It's a central idea in the development of efficient solution methods for linear programs, like we're going to see later on in the course. It's specific Benders decomposition and column generation. So let's have a look at the theorem first. So the resolution theorem looks like such. So assume that you have a polyhedral set represented like so, like we've been doing so far, by a finite number of constraints defining half spaces. And we know that that defines a convex set. It's a polyhedral set, as we defined, and it has at least, let's assume that it has at least one extreme point. So if you call the collection of extreme points X and a collection of extreme rays W, then we can find an equivalent representation for P named Q, which is given by the convex combination of your extreme points and the conic representation of your extreme rays. So that means that, remember that these are both linear combinations, and we've seen convex combinations before, and then I'm calling these conic combinations because, you know, they are just linear combinations with a non-negative term, with the skeleton being non-negative, which form the cones like we discussed in the previous video. Of course, this has a theoretical relevance, but in practice is not very useful because while this is much more manageable in terms of, you know, representability and having a finite number of them, this representation will require us to know beforehand what are all the extreme points and what are all the extreme rays. So this is explicitly utilizing the extreme points and extreme rays, while this is implicitly representing the extreme rays and extreme points. So in terms of practical use of this, there are not many contexts where this becomes useful. There is, however, two very important contexts when they are useful, and that is when we're talking about Benders decomposition and column generation. So we basically use the idea that we not necessarily need all of the extreme points and extreme rays, but we only need those that are associated with the optimality of the problem P, the problem P formed over the polyhedral set defined like so. So if we had only like those extreme points and extreme rays around the region where the optimal actually is, this is all we need. We don't really need the others. So we'll see that we can exploit this formulation in a sense that we are gradually building it and hope that we don't have to build all the way to the end. So I wanted to leave this here because this is going to be important for us in the future, and I think it's a good finishing point for the first part of our course. So here are some remarks. Theorem 8. By the way, I'm not giving the proof of the theorem. You can find the proof in our textbook. It's not that involved, but it didn't really have anything that we need for what's coming up. So I'm just leaving it without proof. And if you're interested, have a look at our textbook. Basically, you can find this in any linear programming textbook, really. But one interesting corollary for this theorem is that when we talked about convex holes, I think at some point I said something on the lines that if you have a bounded polyhedral set, you can represent it by the convex hole of these extreme points. So if you think of a polyhedral set that looks, say, like so, I don't know, kind of like that, then if you get the extreme points and write its convex hole, you obtain the same set. And the reason for that is associated with this. Just think of the resolution theorem without this term and without this term, because a bounded polyhedral will have no extreme rays, will have no rays. So that's it. Which is, that's something that you can prove using this But I think that the most important consequence is this. It basically means that we have these two alternative representation for polyhedral sets. One where you implicitly represent all extreme points in extreme rays with a finite number of constraints defining half spaces and looking at the intersection of them. And the alternative representation is doing linear combinations of the extreme points in extreme rays in specific convex combinations of extreme points and conic combinations of extreme rays. It's pretty cool. So just to finalize and try to bring an illustration for everything we saw in this video and in the previous one as well, I sort of prepared this example. So basically we have this polyhedral set defined by these two constraints and the non-negativity conditions. So this first constraint is this one. That second constraint there is this one. So my feasible set is all there, right? And then if you think about the polyhedral cone associated with this polyhedral set, you can just think about, making this 0 and making this 0 and think of the directions that it causes. So you get these constraints, this one, and these two, right? Just so reorganizing things a little, you can see that this constraint is redundant because these two are greater or equal than 0. So this constraint is kind of like the relevant one. And then D1 becomes greater than 0, greater or equal than 0 becomes redundant because we have this first one saying that is greater than D2, there you know that is greater than 0. So you can write the whole polyhedral cone with these two constraints, D2 greater or equal than 0 and D1 greater or equal than D2. The reason why I'm cleaning up of redundant constraints is because I want to show you that effect of finding extreme rays for that. So an extreme ray for this would be a ray, would be a ray at which this is R2. So one of the constraints is active and -1 constraints are active. So one constraint being active is when this is 0. So D2 is 0. So D2 is 0. This has to be 0, 0 is not really helpful. So we need this greater than 0. So, and because any extreme ray scaled is the same extreme ray, we can put just 1. So we get this one there. And the other case is when these two are equal. So this second constraint is active. And that means that D1 equals D2. And that's the other extreme ray. So these are the two extreme rays in this polyhedral code. And you can kind of see what they are in the picture, right? So, first constraint, second constraint. If I look at this vector 1, 1, it's exactly this direction. Of course, I'm putting here next one because that's the relevant kind of direction, but this direction is unbounded anywhere in the code. Likewise, W2 is here. So anywhere in the code, this direction is unbounded as well. So if I put these two together, anywhere I chose this point, I get my recession code, like we saw. So this thing there is our rec of P. There. And any direction in here is a ray, with these being extreme ray. Sorry, these being extreme rays. Another way of seeing the recession code is, remember that we define it in this case to be something that would be like so. So if you think about the constraints, so constraint 1 has associated the vector 1, -1. So it's this vector here. Let's call this A1. This vector here is A2, the vector 1, 1. Because I want things greater or equal in both cases, I want this region. And then you have two other constraints, that x1 greater or equal than 0. So x2 greater or equal than 0. So the vector is the vector 0, 1. And x1 greater or equal to 0, that gives us 1, 0. So this is A3 and this is A4. Now, if you put, I'm going to move them all to the same point, say here. So I have A1. I have two A1s, sorry. A2, like so. And I have A3. And I have A4. And I want all the vectors that form an angle no greater than 90 degrees with them all. So basically what I have to do is the intersection, right? So above this is everything that forms an angle no greater than 90 degrees with A3. To the right of this is everything that forms an angle no greater than 90 degrees with A4. This is with A2. And this is with A1. So everything that is in there, everything that is in there, everything that is in there, and everything that is in there. So you can see that when you look at the intersection, you get exactly this bit, which is again the recession cone. So that's that representation we had in the past before. And the last thing is that now, if I get a generic point in my set, I can represent this point by, say, a combination between extreme point x2, which is this, 1, 0, sorry, 0, 1, and the extreme rays w1 and w2. So basically this is saying start from x2, move along x1, w1, then move along w2. So start from here, move along w1, then move along w2, and you get to the y. And of course, this is not a unique representation, right? So you can also say, you know, make a convex combination of two extreme points, so half and half, x2 and x3. And then you add 3 halves of direction w1, which gives you, again, the convex combination of these two with half gets you to this point. And then you do 3 halves of in the direction w1. So 1 half and then 2 halves, and I get there again. So I can represent any points of this set by doing these combinations. So that's it. Hopefully that was clarifying in terms of the representation theorem and that part related with extreme rays and cones. And see you in the next lecture.